So today we're going to continue on our design and implementation of this linked list. Last we left off, we had done the two add methods where we were adding it to the end of the list and then we were adding it to the beginning of the list. And now we have three remaining to fulfill the interface design that we originally had with our array-based list. And those are going to be actually super easy because we already did the groundwork to get an arbitrary node at an arbitrary index, right? So let's go ahead and continue with what we need to do. And I know what I need to do because I've got a bunch of to-dos in here. I reminded myself by throwing a runtime exception and also by putting it into comments here. Over here, there's a nice little, tick mark here that tells me that I've got a note here that I need to do this, all right? All right, so let's go ahead and get the element at the given index here. So instead of throwing an exception, I'm just going to go ahead and call this function down here that I wrote and say this dot get node at that particular index. Because once I've got that node at that particular index, I can go ahead and get the element and simply return it. Right? In other words, because I did all of that grunt work to build some building blocks for this and did this get node method, now this turns into a one-liner. Right? Let's go ahead and make sure that it works by coming over here to the demo class. And remember that I've added a bunch of stuff. Let's go ahead and restore this so that I add a bunch of stuff at the end. And let's also go ahead and print it out because I want to see what it looks like before I test this. So 42, 8, 35, 2, and then 10 through 100 by tens. I'm going to go ahead and create a for loop here for int I equals 0. I is less than list dot size, right? I plus plus. Because I'm going to have a traditional for loop here that simply just says system.out.println list.get the ith element. Right? Now, one problem here is that do I have this size method? Now, that seems like it would be, it's not compiling because I don't. But it seems like that would be pretty convenient to do. So let's come back over here to my linked list. And remember that we are keeping track of this size. So I'm just simply going to have a getter for it. Public int get size, or I'll say size. Right? Return this dot size. I could call it get size or whatever, but I'm just going to call it size because that's what the list interface in Java does. Right? So let's go ahead and do that. 42, 8, 35, 2, and then 10 through 100. Looks like it works to me. Except that I was only testing what I expected to be correct, right? What I should do is I should test corner cases. So for example, what happens if you try to ask it for the negative first element? What happens if you try to ask it for an element that is way beyond the bounds, 1000 here, that you should not be asking for? Let's find out what happens now. Null pointer exception. Cannot invoke get next because current node is null. Again, do you see any nodes here at all in the demo class? No. This is another leaky abstraction. And it's a leaky abstraction because we never did any proper error checking here. Right? So do some basic bounds checking. Right? In fact, we're probably going to want to do that here. We're probably going to want to do that here as well. We already did it up here, but in a different way. Right? So this sounds really familiar. Didn't I do this when we did the array-based version of this? In fact, didn't I put it into a function? I'm going to go ahead and steal that function now, right? And put it over here into my linked list. Before I go on, though, copy, paste, copy, paste, copy, paste. Does that sound like a good pattern to follow? Right? Now I've got repeated code in one type of list and repeated code in another type of list. Remember, both of these things implement this interface that we did last time. So let's take a look at what this looks like from an object-oriented programming perspective. Up here we have a pure interface, my list. Right? This is an interface. Down here we have my linked list that we're currently implementing. And over here we have my array list. And in both of these, I have bounds checking. I am keeping track of the size using a variable. I have a getter for the size, right? that sounds like I'm repeating a lot of code over here and repeating a lot of code over here. So my first thought is, well, what if I promote them up to this interface? Can an interface have code? It's a pure abstraction. Asterisk, as of a few, maybe like 8 Java versions ago, they did make it so that interfaces can have what are called default methods. It was a bad idea at the time, and I'm not even going to entertain it now, right? But anyway, that doesn't sound like an interface to me. That sounds like something in between, say an abstract list. Remember, it's a halfway point between all of these things. So I'll say that this implements that, and then this inherits from that. So that I can take anything in this class that is shared with this class, and I can move it up to this abstract list so that these things can inherit that behavior. Right? Those 3 things that I mentioned, anything that's in common to any of those things would be a candidate for putting it up here in abstract list. I'm not going to go that far. Instead, I'll leave that as an exercise for you to consider. Right? But I do want this bounds check here, because if you ask for something negative, if you ask for something of the size, remember that if there are 5 elements in there, that's 0, 1, 2, 3, 4. You ask for the 6th one at index 5, that's an error. I'm going to do this bounds checking up here as a preliminary check before not remove, but here we go. Do some basic bounds checking. This dot bounds check of index. Right? I'm not going to repeat that code in the class, and I certainly don't want to repeat that code between classes. So the solution, once again, is to create an abstract list and promote that stuff up. Okay? Object-oriented programming, right? Let's go ahead and continue with this one now. I'm going to remove this element. Actually, let's do this one because it's easier. I'm going to replace the element at that index with x, and then I'm going to return the ultimate that value. So first of all, let's do some bounds checking here. Okay? What do I need to do now? Well, I need to find it, node t, node, this dot get node of index. And note that I do know that this is a correct index because my bounds check would have thrown an exception if it's not. Right? Otherwise, now I've got the node, what I can say is a node dot get element, right? Because I'm going to save that off into a temporary variable, and ultimately I'm going to return that, return temp. And then I can say node dot set element to x. Or not set next, but set element, sorry. There. Oh, we don't have a setter. That's okay. Let's go ahead and refine our interface now. So let's go ahead and go back to this node class and see, I've got a getter for the element, I've got a getter for the next, I've got a setter for the next. Maybe I now want a public void set next. Or not next, but element. Key element. I shouldn't be typing any of this. Remember that you can generate this code by going up to source, generate getters and setters. This dot element is equal to element. But I'm a fast enough typer, I'll just get it done. Besides, I want to do this in a different way. Even if I put this set element here, over here in my linked list, that's still 3 lines of code. Oh my God, 3 lines of code. Right? Let's get this down so that we only have 1 line of code. In fact, 4 lines of code here. I'm going to get this down to 1 line of code. How? Well, you want to set the element. What if we replace the element here directly? What if I had a public t replace element, t element, and I did all the work right here in the node class. T temp is equal to this dot element. This dot element is equal to the element that you've just given me, element, and I'll return temp. Right? In other words, I'm doing, 3 lines of code. I'm not going to get away with that. But ultimately over here in my linked list, I don't have to worry about all those details. I could say return, oh, I guess I do need to get the node, right? I can then say dot replace element with x, and I'll return it immediately. Return. I can still get it down to a 1 line of code here, right? This is generally referred to as chaining, right? This dot get that node. Dot replace that element, right? I'm chaining these things together. This is getting close to something called a fluent design pattern, where you can just chain commands together. We already did it. In fact, the string builder has that, that kind of pattern there. What I can do is I can say sb.append, hello, right? Dot append, goodbye. Dot append, dot append, dot append as many times as you want. I can chain all of these things together. It's a really nice, convenient pattern to use. Right? And I've used it here to great effect by getting 4 lines of code down to 1 more readable line of code. I will get the node at that particular index and get that element, and then I will get that node at that particular element index, and I will replace the element, returning that value. Really, really convenient stuff here. All right, the last one, remove an element. All right, we've got to be careful here. Right? All right, so suppose that we have a list that looks like this. Right? Here's the head, and we want to say remove X right here, whatever is in it. Right? So I want to remove this one. How do I go about doing that? Visually. Right? Well, it involves me simply just taking this and moving over here and then throwing it away in the dustbin or whatever. But what happens to everything after that list? Right? We don't want to lose that stuff. We don't want to just take the list and chop it off right here and then throw everything away. Right? We want to preserve this thing right here. Okay? So how do I go about doing that? I need to make sure that this now points to this one over here. Right? It's really, really long, so what I'll do is I'll go ahead and say that undo, undo. I'll move it down. Right? And now that one down here is effectively removed. Right? Let's go ahead and reverse this. Okay? So I want to remove this guy right here. What is my first step? Well, I have to find it first. Find the one that you want to remove. I've got a get node method to do that for me. But is that going to help me to make this one point to this one, circumventing this one right here and deleting it? Nope. I want the one right before it. I'm going to call that previous. I'm going to call this current. Right. This is the one that we want to remove. I want to hold the previous here because I need to make previous point to current's next to get around it, basically. Okay? If I just have this current right here, can I work backwards? Not with this design. There are things called doubly linked lists that we'll mention here in a second, but mine's not a doubly linked list. Instead, I can only work one direction. I can only work forward here. So my strategy will be to find the previous, because if I've found the previous, can I get the current? Yeah, it's the one right next to it. Right? So let's find the previous first. Right? So first of all, 0, do some basic error checking. Right? That's going to be this dot bounds check, bounds check on index. Right? I'm going to let it do the work for me. And now I need to find the current, the previous node. Right? Previous, I'll put that in quotes there. Right? So node t previous is equal to this dot get node of index minus 1. I'm going to stop short. Okay? And now I can get the next one, or the current one, is equal to this, or not this, but actually this dot get node at index. Right? Now suppose that there were 1,000,000 things in that list. I have to start at the head and traverse all the way to that until I get to that index 1,000,000 times, say. To get the current, I have to start at the head and traverse it another 1,000,000 times. In other words, 2,000,000 things. Is that the way to go about doing it? Or if you've done 1,000,000 things already, it's much easier to just do one more thing. Previous.getNext. Right? So now I'm not doing 2,000,000 things, now I'm doing 1,000,000 things instead. Right? All right. So I should have outlined that. 2, find the current node, the one to delete, right, to remove. Right? All right, once I've got that, what do I need to do visually? I need to make the previous point to the current's next. Right? So 3, make previous point to current's next node. Again, visually what this is going to end up doing is I've got previous pointing to current, pointing to, I don't know, next. And I want to make it so that previous now points to next instead, effectively circumventing this current and getting rid of it. That's a one line of code. Previous dot set next to current dot get next. That's it. Right? The previous is going to set their next to the current's next. Right? And that's it. What else do I need to do, though? Careful. If you have 4 elements there to begin with, and you deleted one, how many do you have left over? 3. Remember that I was keeping track of that in a size variable. Anytime that I added something, I incremented size. Right? Add something, I increment size. If I'm going to be, if I get something that's not affecting the size, if I am replacing something, there are 5 elements before, yeah, there's one missing now, but then you add it back in, there's no change in the size. And so now what I need to do is I need to say size minus minus, right? Just to make sure that size is still correct. Uh-oh. Remember we have this, this return type here. It removes the element from the given, shifting all elements down if necessary. Actually, I'm going to get rid of that because they're no longer shifting in a linked list. It removes the element at the given index and returns the element that was removed. Ah, that one-liner is not going to do it for me. But guess what? I still have access to the current node. I can go ahead and say return current dot get element. All right. Cool. Go ahead and clear that out. Let's come back over here to demo and make sure it still works. Invalid index, yay, that's still happening, so I'll go ahead and get rid of that now. All right. I'm going to go ahead and get rid of this too, because I know that everything works up to that point. There we go. So let's go ahead and remove something. All right. So list.remove. I don't know. Let's remove the 35. So remove the element at index 2. Let's make sure that it's correct too. System.out.println list.remove. Right. Remember, I'm not removing the number 2. I'm removing the element at index 2, which is going to be Justin Steele right there, 35. Right. So I'm going to expect that 35 gets printed. And if I print the list after I'm done, 35 will now be missing too. And it is. It's gone. Is that sufficient testing? Just testing one thing? Nope. Let's go ahead and test 1. Oh, okay, that works. It removed 8. Right. Is that enough testing? I need to make sure that the corner cases work. What's one corner case? Removing the first element. In other words, removing 42 in this case. Did it work? Nope. That's one of those corner cases that you're probably going to have to deal with separately. View this again. I'm going to go ahead and get rid of previous and current here. One of those special cases means that you have to remove from the head here. That you're going to remove this guy right here. Right? Is it going to work just to, make whatever the previous is here, which doesn't even exist, point to this one? No. What do I need to do to make it so that the head is removed? I need to change what the head is referring to. Move the head over here. Come on, there we go. And you've effectively removed the first element. So if you're removing the first element, the element at index 0, that's a special case. Do some basic error checking. After I've done that, let's go ahead and check. So 0.5 here, right? If removing from the head, right? In other words, index is 0, then I will do something special. If index is equal to 0, I will say this dot head is equal to what? This dot head dot get next. I'm just advancing it one over, just like I did over here in my visualization. Before it was pointing here, and now it's pointing here. Head dot get next, and then I change the head to be that thing. All right, and don't forget this dot size minus minus, right? And then I can return. What am I going to return here? I've already lost reference to the old node. So what I'm going to do is I'm going to store that. Node t old head is equal to this dot head, so that I can update this head, so that I can say that old head dot get element. That's what I'm going to return. Okay. What about the rest of this stuff? You could go ahead and reorganize this so that it's an if-else statement, right? And then get rid of some of the redundancy. For example, the decrement here is done twice, right? It's not actually done twice. It's done. It's repeated code. You can go ahead and make this as smart as you want to reduce the number of lines of code. This is just a demonstration. So let's see if it works now. Remember, we were trying to get rid of 42, and it looks like we did. What is the other extreme case that I should probably be testing? Remove from the end. We call that the tail. I think it's 13. Yep. 100 right there. And it worked. What happens if I try to remove something that doesn't exist? 14. I should be getting an exception. Great. Invalid index exception. No leaking of information here at all, right? What if I try to remove something that doesn't exist on the other end? Again, invalid index exception. Right? This looks like a pretty solid implementation. I would want to go back and clean this up, document it, update the documentation as necessary, probably go back and rethink my inheritance hierarchy so that it looks something like this to reduce the redundant code, and of course, clean it up so that I've reduced redundant code throughout this entire thing. Right? Good question. For which one? Remove? Let's find out. So I'm going to have to get rid of all of this testing, right? Delete it, right? Restore it later on, right? This is why we want formal unit testing using JUnit or something. Let's go ahead and try to remove it. So list.remove, no, you want one thing, right? All right, so let's go ahead and add one thing. Come on, undo. There we go. Add one thing, list.remove 0. Oh, okay, no exceptions. Maybe it's correct. Let's find out. If I print it, I'm expecting what? An empty list? And that's what I got. Let's verify that our size still works. List.size. That should be 0 at that point. Yay. Why does it work like that? Remember, if you're removing from the head, then you're getting the next. The next happens to be what then? Null. Right? So that's how we empty a list. Right? There we go. Whole bunch of other secondary functionality that you can add here as well, right? You can add support for the tail element. Right? You can add batch methods, right? Say clear. What else? Add all, right? Remove all, right? The same stuff that you could have done in the other one is going to be the same stuff here, right? That you could have a copy constructor that allows you to create a new deep copy. You could compute a sublist. You could add functionality to shrink the list if necessary, right? Actually, we don't even need to do that. That's going to be a secondary functionality of an array-based list. Otherwise, what you can do is go even further and look at what are called variations on this theme, right? You can support doubly linked lists, right? Where you have each node has a next and a previous, right? What would that look like? Where's my doubly linked list? There we go. There we go. It looks something like this, where on a particular node here, 6, you can work forwards as usual, or you can work backwards, right? That means that you can keep track of the head element and the tail element and then zigzag all you want, right? It makes some things a little bit easier. It makes things a little bit more complicated, because what would you have to do if you wanted to delete 6 now? What if you had a doubly linked list like this? Come on. There is 6, and it's got forward references and backwards references. And there are backwards references and forward references to it. Now I've got to delete this, I've got to make sure that this one points backwards, that this one points forwards. So in other words, I've doubled my work. Doubly linked list. But in other respects, I've reduced my work. So maybe it's a wash. You do have to be careful here, because how do you know that you're at the head? Now if you're going off the list that way, you need to make sure that there's a null pointer there as well. So that might mean that you keep track. You can keep track of a tail and a head element. Right? You can write what are called circularly linked lists. Right? So here's an example of that. These are just visualizations. Right? There we go. There's a circularly linked list. You may not even have a head in that case. You just have a current node. Because you get to the end, is there really an end? Nope, it just goes right back to the beginning. Is there a concept of an index anymore? I don't know. Right? This is just another data structure that might have its own uses, like a round robin kind of thing, where everybody takes their turn, and then once everybody's had a turn, then you start over again. Right? That's kind of round robin way of doing things, or like a token ring network. Have you ever? Nobody probably has ever set up like our Wi-Fi is too good now in 2024 to set up a local area network. Has anybody still done that? No, for gaming, to reduce lag, right? Well, it used to be that on a token ring network, you would take a piece of coax cable and plug it into a computer, plug it into the next computer, plug it into the next computer, and you make sure that it plugs in back to the first computer. Because the way the network works is by going round to each computer. Now is your turn to talk and send everything to the network. Now we give you a token, and we start right back down to the beginning. Does anybody still set up LAN stuff for large gaming stuff? Yeah, it's still over the network. Like, so it's not. Yeah, yes. Okay, just because you want, competitions will usually do this in order to make it so that. Oh, once a month for fun. Okay, just for fun, right? But probably you don't use the coax anymore. I haven't even seen a network card that takes coax. Okay. Okay, all right. Yeah, it's not a thing anymore apparently. You could also do what are called skip lists. This is a hybrid between the two, right? So you can see all these arrows here. They're kind of basically a linked list, but we also have locals, right? So this is a linked list, and then you can jump from the first element to the third element, or you can jump from the first element all the way to, the first element all the way to the fourth element, and from the fourth element you can go to the sixth element. If you've ever been in a major city, you have say subways. And you want to go from point A to point B. There are generally two options. One of them is the local. The local is going to ensure that you stop at every station along the way. That ensures that every station is reachable by the subway or by the tram or by the bus or whatever. But then you have alternative buses that are expresses that do not have to stop at locations 2 and 3. Instead, you can be picked up at location 1 and jump immediately to location 4. Maybe that's not your stop. Maybe your stop is location 8. So you would take an express from location 1 to location 6, get off, then get on the local so that you can hop over to just 2 more stops to station 8. That's what the skip list is doing. You're allowed to skip things, right? Unfortunately, it gets very, very complicated because if you do end up getting down here to just everything is connected, that's just a regular old linked list. If you start skipping it so that everything is reachable from everything else, now the topology of what your skip list looks like, everything is connected to everything, right? And you're kind of you're not getting any of the benefits of the express because now every bus stops at every location, or now you require actually n-squared buses. You require so many buses for every single possibility that it's just not doable anymore. Right? So it's a delicate balance. You also have another hybrid called an unrolled linked list, which is a hybrid between an array-based list and a linked list, where you have a head here, but each node does not just contain one element. It contains an array of, say, m elements. Right? And then that has a reference to the next, right? And then the next contains m elements. And then the next contains, m elements, so on and so on and so on, right? That gives you kind of a hybrid balance between something that looks like a pure linked list and something that looks like a pure array-based list. It's something in between. It has some of the benefits of one and some of the benefits of the other, and some of the disadvantages of one and some of the disadvantages of the other. Yeah? They don't necessarily have to be, but it's generally what's done. Generally what you do is you choose an M so that it fits in one page of memory to reduce cache misses. And so this M here is tunable, and you generally don't want it to grow or shrink. You want it to be tuned to that particular system. You don't, no. In fact, you wouldn't. If there's only 81 in there, you would have an array that has a capacity of M elements, and then just 81 is in there. Right? So each one of these would be basically an array-based list, and then that's your node instead of the node that has a previous, next, and an element. In fact, what would it look like? Let's go ahead and look at our node class again. Right? Instead of, you do have a next here, but instead of this thing right here, what would it look like? Private T elements. Right? Instead of this thing right here. It looks something like that. Right? I don't want it to look like that, but that's an unrolled linked list. So again, you've got an unrolled linked list where each node is an array of elements, not just one. And then you also have skip lists where you can skip. It gives you a little bit of random access, the benefits of random access, but like with an express train, but you also have to have all the locals in order to get to everything. So those are all of the variations, or that's not all the variations, there are other variations. And in fact, the other variations that we're going to start discussing in detail are stacks and their cousin, queues. Right? Let's discuss stacks first, though. Right? What are stacks? Stacks are a restricted access data structure. Right? So collections, such as lists, sets, etc., are unstructured. Right? They just hold stuff. Right? Now, lists are going to hold stuff in an ordered manner, right? There's the first element, the second element, the third element. Sets are going to hold them in an unordered manner. There is no such thing as a first element, second element, or last element, but they just hold stuff, right? Unstructured. Let me spell that correctly. There we go. You can impose a structure on, say, lists by sorting them. Right? You rearrange the list so that they are in order, right? But that's imposing an order, right? That's imposed on the data structure's state. Right? When we talk about data structures, there are two elements to that. Remember encapsulation, object-oriented programming principles. Every object has state, which I'm talking about here, that we impose it on the state. But then the other thing that they have is behavior. In other words, the methods, right? The alternative is to create structure through an object or data structure's behavior. It's publicly available interface. Right? In other words, it's public methods. Okay? So that's the alternative way. That's what we're going to do with a stack. A stack does this by restricting how you interface with it. Right? There are only two basic operations. Let me rephrase that. Basic operations. Right? There's a push and there's a pop. Right? The push is adding an element to the top of the stack. Right? The pop is removing and returning the element at the top of the stack. Right? You've probably seen stacks before, especially if you're talking about a call stack. When function calls function, calls function, calls function, you have what's called a stack frame. Right? All the local variables are stored there. The return value is stored in that there somewhere, right? And that is the stack space. What happens when you fill up the stack and it overflows? You have something called stack overflow. Right? Let's take a look at a picture of what this looks like. Now, I said top of the stack. So we're going to depict it as this bin right here. This is going to be the bottom, and that this is going to be the top. So that you only ever interact with the top of the stack. You can take elements, say 42 here, and you can place them in the top of the stack, and that is called pushing. You push onto the top of the stack. You can take elements off the top of the stack, and that's called popping. Pop, right? Remove and return elements. Right? When you do that, it makes sure to retain the ordering. So if I'm going to put 42 in here, it gets placed right there. If I'm going to put in, say, 35, there it is, then I need to push it on the stack, and that's now at the top. If I'm going to add another element here, say Imanaga there we go. We'll push it onto the top, right? There is structure in how you interact with it. You can only ever push at the top. You can only ever pop at the top. Now, why do we call this a stack? So when I say the word stack, what comes to mind? A stack of fill in the blank. Fill in that Mad Lib. A what? A stack of papers? Okay. I'm thinking of something more fragile than papers. Go to your cafeteria, right? What do you have? I need to get some food. What am I going to do? I'm going to go over to the stack of dishes and pull one off the top. Are you going to go to the stack of dishes and pull one off the bottom? What happens if you try to do that? They're all going to fall over. Are they plastic over there? They're probably plastic, right? So they may or may not break. Who knows, right? But in any case, you're not going to do that, right? Okay, now you're done with your... the dishwasher comes out with all the clean plates. Are they going to try to insert it in the middle of the stack of dishes so that people can take them? No. What are they going to do? They're going to put them at the top. In fact, this mechanism here this is where we get the name stack, I believe, right? There's a little spring mechanism here so that when you push the dishes down, in your cafeterias, you've got this mechanism. You can push the dishes down, right? And it holds them like that. It goes down so that you're not reaching to the top of a stack like this. It's been many years since I've been to that cafeteria, but am I just talking nonsense? They have dishes there, right? It looks like this, right? That there's some sort of mechanism that gets pushed down, and then this spring will make sure that they're always at the top. So what are you going to do to the dish? You pop it off the top. Because there are these little tabs there that hold the dishes in instead of just springing out, there's not? Oh, okay. Maybe it's just the weight that does it then. But there used to be these little things so that you'd pop it off, all right, and then make a little sound, right? And that's where these terms come from. You are pushing it to the top of the stack of dishes. You are popping it off the top, right? And there's this little mechanism down there. There is a spring, right? Oh, there's not? Okay. Maybe our cafeterias are not that sophisticated anymore. Anyway. All right, so that's where it comes from, though, if you've ever seen those at like a Golden Corral. Or they have them at the Amazing Pizza Machine, right? Go to the Amazing Pizza Machine up in Omaha, and they've got these things there, right? But in any case, that's what it looks like. You are only allowed to, you are only allowed to work from one end, pushing things and popping things. All right, if I have pushed 42, 35, and 18, my push order was 42, 35, 18. What if I start popping these off the top? What is the first thing to come off the top of the stack here? 18. So if I start popping, my pop order is going to look like this. 35 comes off the top, there we go. And then 42 is down at the bottom, and it comes over here. What is the relationship between these two things? They're reversed, right? This means that it's a LIFO data structure, right? So stacks are a LIFO, which is last in, first out data structure, right? This is ensured behavior through the public interface, right? You are generally, I should say, not allowed to interact arbitrarily with the stack, right? You know, no pulling out from the bottom of the stack of the dishes, knocking them all over, no shoving it in the center somewhere so that you're knocking them over or risking that, right? Let's come over here and think about what a stack implementation would look like. Again, following that process of let's think about the interface. Then we think about the tests. Then we think about the actual implementation. So let me go ahead and create a new class here called stack. And I want it to be able to hold anything, not just strings, not just integers, right? I want it to be able to hold t's, whatever t is, okay? Let's worry about the state here in a second, right? Public, push, right? And public, pop, right? Pop, right? Let's define push first. Well, first of all, I need an element to push, right? T, and I'll just call it element, because that's what I've been doing up to this point, right? So adds the given code element to the top of the stack. I'll worry about the implementation next time. What should pop look like here? Removes and returns the element at the top of this stack. There we go. So I need a return type. That return type is going to be T. Would it make sense to allow this? Public void insert, right? Tx at index, int index I, or int index. That's all I need, right? Is that an appropriate method for this class? Arbitrarily insert x to any old index that you want. What does indexing even mean anymore, right? When I drew my picture, I drew it like this. Is the index 0 down here, 0, 1, 2, 3, or is it up here, 0, 1, 2, 3? I'm not sure. I don't even know what that means. But should I be able to insert at an arbitrary location? Right. Does that sound like a good method to have as part of the public interface? I don't think so. Remember, this is a stack. If you're shopping for a data structure where you can add an element to an arbitrary index, remove an element from an arbitrary index, you are shopping for a linked list, or more generally, a list. Right? This is a completely different data structure. This data structure is a restricted access data structure. We're only going to allow you these two things. By the way, what does it mean that it's top or bottom? Right? I drew it like this because I use the words top or bottom. But if I were to take my computer and turn it upside down, does that make the top the bottom and the bottom of the top? It's just a concept, right? It's just a concept of what it means to be the top. It's from one end. The other one is the other end, right? It doesn't matter how you orient it, okay? All right, let's think about the tests for this before we come back and finish that off. Right. I'm going to want to create a stack of, say, integers, right? S is equal to new stack of integers. S.push 10. Actually, no, let's do the example I just did. 42, then we'll push 35, and then we'll push 18. There we go. Why are you complaining? Probably because it's not stack. Which stack are you? Yeah, it's my stack. Push. Yeah, you are. There you are. It's probably just because it's not compiling. And then I'll go system.out, system.out.println, s.pop. Right. So what am I going to expect here? If I push 42, 35, 18, what's at the top of the stack now? 18. If I pop again, I will expect what? 35. If I pop again, what will I expect? 42. Oh, careful. What if I pop one more time? Here's your empty stack. What happens when you pop on an empty off of an empty stack? What should happen? Ideas? Nothing? Returns null? It throws an exception? There are lots of options. We'll consider them all for next time. Right? But otherwise, we're going to end early today because it's only like 5 minutes early. But remember that there is the student advisory student advisory panel going on right now for the last 15 minutes and all the way till 1 o'clock over in Avery 348. It's your opportunity to express your opinions, learn more about the department, its curriculum, facilities, faculty, learning assistant program, everything about it. If you want to have more information about the department, you can go ahead and go over there. And there is, I believe, $500 worth of pizza over there, whatever that buys you at Papa John's nowadays. Right? So I'd encourage you to head on over there and check it out.